Swayam Prabha. Digital India. Educated India.
Hi, let us start now. The first module or the chapter of the course, introduction, is divided into three parts. So let me go first with the just overview of the objective of the course, this particular module. So we'll start with the review of the metric units, and we'll go through the basic concept of system, state postulate, equilibrium and process in this part of the module. So what is thermodynamics as such? It means heat. This is a heat, and its dynamics is the power. So it's conversion of the heat to the power, and it's like one form of energy to another form of energy. So essentially the thermodynamics turns out to be a science of energy and energy transformation. It has become a fascinating branch of engineering and science because it has a wide application in many aspects of our life and engineering applications. So just take an example. We can take an example from a household daily life. So this is a simple mixer, and here you can see that we use it in a daily basis, and this converts electrical energy into mechanical energy. And this is an example of a room heater which converts electrical energy into thermal energy. So let us take a look at what fundamental laws of nature tells us. By taking an example. So this is a rock on a cliff having a potential energy, and it falls. While going through this fall, it converts its own potential energy to a kinetic energy, keeping the energy of the system constant, assuming there is no loss to the air. So this becomes or this is the fundamental law, which we call it the first law of thermodynamics, where energy cannot be created or destroyed, can change only its form. However, this particular law does not clarify that any process can occur in a certain direction. Spontaneous process we are aware of occurring at a specific direction. For example, we can take a hot coffee mug and keep it in a room temperature. We know that the temperature of the coffee slowly decreases, or the coffee mug cools off. So this is we call a spontaneous process. It has a specific direction, and we are aware of that heat flow in the direction of decreasing temperature. However, if you take a cool coffee mug and put it in the same room, it does not automatically gets heated, and that we know that. So a process has a specific direction. Okay, and this particular aspect is not covered in the first law. This is covered in the second law, which talks about the quality and as well as quantity, and it tells the process occurs in decreasing quality, and this is something which we are going to learn in this particular course. Take another example. This is an example of heating coil. So you use electricity to generate heat, okay, but the other way around it doesn't occur. For example, you provide heat, the electricity doesn't get generated. Okay, so this is something we are aware of that, and hence a specific process occur in a certain direction and not in the reverse direction. A process to occur should satisfy first law and second law, and this is something which is the basis of this course, and we are going to learn more in detail in the rest of the course. Discuss a bit about engineer's role. Now, if you are a mechanical engineer, chemical engineer, or electrical engineer, or any form of engineer, your main aim is to design and develop new processes, improve the existing process efficiency, and while doing so, you come up with a lot of questions. Okay, let's look at an example here, which is the production of ammonia. Now, ammonia is a basic ingredient for fertilizer. You know the reaction from chemistry. So it's N2 plus 3S2 goes to NS3 has a certain temperature and pressure. Now you would like to design a plant or design a flow sheet where you can operate such kind of reaction and produce ammonia. So what are the sources of the required raw material? You need to separate N2 from the air. So you need to compress the air, liquefy it, and separate nitrogen out of it. So essentially you have to provide some energy in order to compress it. So what are the source of raw material? So you have to think about raw material is N2 and S2. Okay. For the case of S2, the hydrogen, you have to do various different options are there in terms of reaction. You have to choose one of them which is most efficient, particularly for your process, because if there are various different possible ways of generating hydrogen. Now in addition, you have to worry about what factors, pressure, temperature, ratio of reactants, and the extent of the reaction depending on the conditions. So you have to worry about that. How much energy is required to compress and raise the temperature of the reactant to the desired level, and so on. So there are many questions which should come as an engineer when you design such a process. Okay. So let's look at the process. So here you have N2 and hydrogen. Let's assume that you have already separated from the raw material. You have got the nitrogen and hydrogen. Now you need to compress it and heat it. That means you need to increase its pressure and temperature to a certain specific temperature and pressure of the reactant. And once the reaction occurs, so here the NH3 is produced, and then you need to use some refrigerant in order to condense it. And once you condense, you can separate in a separator, and the remaining unreactant nitrogen and hydrogen goes back to the initial feed to the reactor. So this is the overall process. However, there are many aspects when you design such things. So how much cooling is required to condense the material, condense the ammonia, and to separate it from the unreacted material? Is this or are there any changes in the phases or the structure of the fluid, whether it goes from gas to liquid and so forth? That is called physical change, or chemical if the reaction is occurring. Is this reaction feasible at the condition which you have specified? So having a knowledge of thermodynamics, which is a study of energy and its transformation, enables engineers to answer all these questions, and hence you can design more efficient plants. Okay, so this is just an example that what are the applications of thermodynamics. This is a steam power plant, okay, where the coal here gets burned, and steam, essentially after this burn, the steam is generated because water comes from here. This is at high pressure, and whatever the remaining gases such as CO2, S2 and so forth goes as a part of the flue gas. Now once you have a high pressure, you pass through a turbine, it expands and does some work. The work gets converted into electricity through generator, and the remaining low pressure steam gets condensed and then recycled here. So this is the overall application which we are going to work on or study in this particular course many times. The important is, of course, various different phase changes occurring, the heat and so forth. So this is a large scale application of thermodynamics. Now you notice that there is a lot of water being used, and hence such plants are very close to river or ocean. This is a real picture of a power plant in Denmark, and this is one of the very efficient plant where 45% of coal combustion gets converted into electricity. So we will talk about the efficiency. Why not it's 100%? What happens to the 55%? So this will come as a part of our second law of thermodynamics. Okay, there are many different applications. So you can see this solar hot plant within for your home is one application you can think of. Refrigerator, the food processing, automobile industry, basic car design, and basic engines, the plane. Then you have power plants. Then you have refineries, where a lot of application of thermodynamics. So let's go to the formal introductions of the course. So we'll start with the dimensions and the units. So any physical quantity can be characterized by dimensions. Okay, this is something we were very well aware of it, and the magnitude is assigned to the dimensions are called units. You can have many different forms of units. So there are primary units or fundamental units. These are something called let's say mass, length, and temperature, time. So these are called fundamental units, and there are other units which are derived from the fundamental units, such as if you divide length by time, it becomes velocity. So these are called derived units. So the velocity, energy, volume, these are expressed in terms of the primary dimensions, and thus these are secondary dimensions or derived dimensions. Now there are many different ways to represent length. You can represent length in terms of meter, you can represent in centimeter. I mean, there are many different ways in different part of the world have tried to make use to represent a length of a let's say a scale. So however, to make sure that engineering divisions or applications, we make use of generic units, a metric standard, international standard system is introduced, and which is a simple logical system on a decimal relationship between various units. So in this system, the length is in terms of meter, mass in terms of kilogram, seconds, time is seconds, temperature is Kelvin, electrical current ampere, amount of light candela, moles. Now many times you have large numbers or very small numbers in the same unit. So for example, you can think of let's say 1000 meter. So 1000 meter, instead of saying 1000 or 10,000 meter, it's useful to use prefixes, and SI units allows you to do that. So the prefixes could be your 10 to the power 12 to 10 to the minus 12, and these are something called prefixes. So you can have kilometer, which essentially is 1000 meter, and so on. So that's the advantage of using SI units. The other important of dimensions is that dimension must be homogeneous. So for example, if you are relating a variable A to B and C, the unit of B and C should be same as A, and that means the homogeneity should be maintained. Okay, so when we apply thermodynamics, we look at a specific system. The system is basically interest or quantity of matter or region in space chosen for a study. So system in this case, for example, is denoted by this region covered within this dotted line, and whatever is outside the system is called surrounding, and the boundary which differentiates surrounding and system is called the boundary. So this dashed line is basically the boundary. Okay, so surrounding, as I said, is a mass or region outside the system. Now boundary is can be physical boundary, can be non-physical or imaginary boundary, and typically it doesn't have any volume. Okay, so the real or imaginary surface that separate the system and surrounding is called the boundary. It can be fixed or movable, and it has a zero thickness or zero mass or volume. So this could be an example of system. So if you are interested to understand the reaction in a reactor, so the reactor becomes your system. You can put this dashed line like this, and you can make this a system. If you are interested to look into the changes occurring in the fluid within this can, then that becomes a system, or the car engine, or the atmosphere of Earth, or the turbine jet engine. So these are all example of systems. Now system is defined into various different forms. You can have closed system, you can open system, you can have isolated system. So let us go step by step. So this is an example of a closed system. So in a closed system, we do not allow any mass to leave or enter. However, energy can cross the boundary. So in the form of work or heat, and we are going to talk about work and heat later on in this course. Now the closed system, the volume may be fixed if the boundary is fixed, but the volume can change depending if you allow volume, if you allow the boundary to move. And this is an example. So you have a closed system where with a movable boundary is called piston cylinder device. So you heat up a system, and this particular boundary will move up in order to accommodate the energy transfer to the gas, and hence the volume will increase here. Okay, so this is an example of closed system with moving boundary. Okay, if you isolate a system such that the heat cannot be transferred to the system, then the energy of the system and as well as the mass cannot be changed. in the sense like you cannot allow the mass to enter, and as well as the energy will not be able to enter if you isolate. So in an isolated system, the energy and the mass cannot enter or leave. So but there are other examples where you need to consider flow, where mass need to also transfer from the system to the surrounding. And this is a common occurrence in engineering applications such as turbine, compressor, nozzles. And this kind of devices involves mass flow, and in such case both mass and energy can cross the boundary of the control volume. Okay, so let's take an example here. So you have this nozzle, and here this dashed line becomes the arbitrary region which we have selected as a control volume. Now this control volume you can choose based on your requirement, based on your proper analysis, and this typically we again will be using the dash in order to signify the control volume. Now here you can clearly see that some part of the control volume is real and some part are imaginary. Okay. Now this control volume would be fixed in shape and size, most common, or it may have also movable boundary. Now this is an example of movable boundary where this particular part of the piston cylinder can change depending on the pressure induced by the flow. So the open system allows mass to flow and energy can also cross the boundaries. So this is an example of a simple water heater where you can clearly see that the cold water comes in and the hot water comes out. So there is a continuous flow here, and hence the mass can enter, and as well as the energy is also transferred for one, because this is a cold and this is a hot, so energy is also being transferred crossing the boundary. So this is an example of open system. So let's take other examples. This is your typical coffee, and you have a Coke here, and then you have a thermos. Now this would be an example of open system. The next one would be example of a closed system. And what about the thermos? So that would be an isolated system. So within the time frame of your interest, there will be no transfer of energy from the thermos to the surrounding. So we can summarize these examples that in case of open system, you have a matter can exchange. In case of closed system, energy can exchange. In case of isolated system, nothing will be exchanged with the surrounding. So in the next lecture, what we are going to cover is we'll define intensive and extensive property and define density and specific gravity. And so we'll see you in the next lecture.